History of the electric battery, 1800 to 1990. The history of the electric battery is not merely a chronicle of chemical combinations, metallic cylinders, and industrial patents. It is the underlying architecture of modern technological civilization. From the moment Alessandro Volta stacked zinc and copper disks to generate a faint, continuous spark, humanity began a relentless pursuit of portable energy that would eventually decouple power from geography. First part of this review conducts an exhaustive deep dive into the evolution of battery chemistry, from its inception in 1800 to the commercialization of the lithium-ion cell in the early 1990s. It traces the trajectory of energy storage as it evolved from rudimentary wet cells that powered the first telegraphs to the high-density intercalation cathodes that enabled the mobile revolution. For centuries, the concept of electricity was confined to the realm of static discharge, brief, violent bursts of energy stored in Leyden jars or generated by friction. It was a curiosity, a parlor trick, or a terrifying natural phenomenon in the form of lightning. The battery changed this fundamental relationship. It tamed the electron, forcing it to flow in a steady, predictable river that could be harnessed to perform work. This transition from static to current electricity was the catalyst for the Second Industrial Revolution, enabling instantaneous communication, automotive transportation, and eventually the digital age. This narrative explores how specific chemical limitations, the formation of hydrogen bubbles, the weight of lead, the crystallization of cadmium, and the volatility of metallic lithium served as the primary constraints on technological progress during the Industrial Revolution and the early electronic age. Conversely, it examines how the resolution of these bottlenecks through material science enabled specific world-altering devices, from the automotive starter motor to the handheld camcorder. It is a story of scientific brilliance, industrial rivalry, and the complex interplay between geology, chemistry, and geopolitics. Scientific Dawn, 1800 to 1859. Taming the Electron. The story of the battery begins in a physiological debate that engaged the finest scientific minds of the late 18th century. It was a clash between biology and physics, vitalism and mechanism, centered on the twitching leg of a dissected frog. Luigi Galvani, an Italian physician and anatomist, had observed in the 1780s that frog legs twitched when connected by two different metals, a phenomenon he attributed to animal electricity. Galvani believed that the vital force of life itself was electrical in nature, and that the animal's tissues were the source of this power. Alessandro Volta, a physicist at the University of Pavia, initially engaged with Galvani's work but soon disputed this vitalist interpretation. Volta argued that the electricity was not intrinsic to the animal, but was generated by the contact of dissimilar metals in a moist environment. The frog's leg, he contended, was merely a conductor and a detector, not a generator. This disagreement, known as the Volta-Galvani debate, was one of the most productive scientific controversies in history. It drove Volta to prove his hypothesis by constructing a purely non-biological device that could sustain an electric current, thereby removing biology from the equation of electricity. In 1800, Volta communicated his invention to the Royal Society of London in a letter that would change the world. His device, the voltaic pile, consisted of alternating discs of zinc and copper, or silver, separated by cloth or cardboard soaked in brine, salt water. Unlike the Leyden jar, which stored static electricity and released it in a single violent burst, the voltaic pile produced a continuous flow of current. This was a watershed moment in the history of science. For the first time, electricity was a steady stream rather than a fleeting lightning strike. Volta's theoretical framework for his invention, however, was flawed. He believed in a theory of contact tension, arguing that the electromotive force was generated simply by the physical contact of the two metals, with the electrolyte acting merely as a conductor to prevent short circuits between the pairs. He viewed the chemical corrosion of the zinc plates as a nuisance, a defect, rather than the source of the energy. It would take decades for the scientific community, led by figures like Michael Faraday, to fully understand that the electrical energy was the result of a chemical oxidation-reduction reaction. Despite his theoretical error, Volta's engineering was sound. The continuous current provided by his pile immediately enabled William Nicholson and Anthony Carlisle to decompose water into hydrogen and oxygen, birthing the field of electrochemistry within weeks of Volta's announcement. However, the voltaic pile was far from a perfect power source. Its operation was plagued by a chemical phenomenon known as polarization, which served as the first major bottleneck in battery technology. As the current flowed, hydrogen gas, a byproduct of the chemical reaction at the copper electrode, accumulated on the surface of the metal. These hydrogen bubbles formed an insulating layer that physically blocked the electrolyte from contacting the electrode. Furthermore, the hydrogen created a reverse electromotive force that opposed the flow of current. The result was that a voltaic pile would work brilliantly for a few minutes, and then its voltage would drop precipitously, rendering it useless until the bubbles were manually cleared or the pile was rebuilt. Additionally, the vertical stack design was mechanically unstable. The weight of the metal discs squeezed the brine out of the cloth separators, causing the electrolyte to leak and creating short circuits between the plates. The pile was a wet device in the truest sense. It was messy, unstable, prone to drying out, and offered a lifespan measured in minutes or hours rather than days. To address the mechanical limitations of the vertical pile, William Cruikshank of Scotland designed the trough battery in 1802. Instead of stacking discs vertically, Cruikshank arranged square plates of zinc and copper horizontally within a wooden box sealed with shellac. The box was divided into compartments, or troughs, which were filled with dilute acid. This horizontal orientation prevented the electrolyte from being squeezed out and allowed for larger plates, which increased the total energy available. Cruikshank's design was significant not only for its stability, but because it represented the first battery designed for mass production. It became the standard power source for early telegraphy experiments and laboratory electrolysis, including Humphrey Davy's isolation of new elements like sodium and potassium at the Royal Institution. While the trough battery solved mechanical issues, the chemical problem of hydrogen polarization remained a stubborn barrier to reliable long-term power. The breakthrough came in 1836 with the invention of the Daniell cell by British chemist John Frederick Daniell. Daniell's innovation was the introduction of the two-electrolyte system, a concept that fundamentally altered battery design. He realized that to stop hydrogen bubbles from coating the copper electrode, he needed to chemically intercept the hydrogen before it arrived. The Daniell cell consisted of a copper pot filled with a copper sulfate solution, inside of which sat an unglazed earthenware container filled with sulfuric acid and a zinc electrode. The porous earthenware pot acted as a semi-permeable membrane, allowing ions to pass through to complete the circuit while keeping the two liquids separate. In this system, the chemistry was elegantly balanced. As the zinc anode oxidized, it released electrons. At the copper cathode, instead of hydrogen ions being reduced to form gas, copper ions from the copper sulfate solution were reduced to form metallic copper. This copper deposited onto the copper electrode, thickening it slightly, but maintaining a pristine conductive surface. This eliminated the polarization effect entirely. For the first time, a battery could produce a constant, reliable voltage, approximately 1.1 volts, over an extended period. This reliability made the Daniell cell the technological bedrock of the Victorian Internet, the telegraph network. Without the stable current provided by the Daniell cell, the long-distance transmission of Morse code would have been plagued by fading signals and unintelligible messages. It was so reliable that it became the standard reference for the unit of voltage, the volt, for many years. The Daniell cell enabled the expansion of the telegraph across continents, powering the communication lines that coordinated train schedules, transmitted news, and managed empires. However, it had its own limitations. It was physically fragile due to the earthenware pot, and it was strictly a stationary device. If moved, the fluids would mix, ruining the cell. Furthermore, it had a high internal resistance, limiting the amount of current it could deliver. Despite these drawbacks, the Daniell cell represented the maturation of the battery from a scientific curiosity to an industrial tool. Rechargeable breakthrough, 1859, the lead-acid system. By the mid-19th century, all practical batteries were primary cells, single-use devices that had to be discarded or chemically rebuilt by replacing the zinc and the acid once their active materials were consumed. This was an expensive and wasteful model for energy storage, comparable to an engine that must be rebuilt after every tank of gas. The concept of a secondary battery, one that could be restored to its original state by passing a reverse current through it, remained elusive until the work of French physicist Gaston Planté. In 1859, Planté invented the lead-acid battery, the world's first rechargeable battery. His design was deceptively simple yet chemically profound. He took two long sheets of lead, separated them by rubber strips, rolled them into a spiral, a jelly roll configuration, and immersed them in a jar of sulfuric acid. When charged, one lead sheet oxidized to become lead dioxide, PbO2, while the other remained pure lead. During discharge, both plates converted to lead sulfate, PbSO4, and the acid became more dilute, turning primarily into water. The brilliance of the Planté cell was that this reaction was highly reversible. By applying an external current, the lead sulfate could be driven back into lead and lead dioxide, and the water converted back into sulfuric acid. However, the original Planté cell had significant manufacturing hurdles. To create the active oxide layers on the lead sheets, the battery had to undergo a tedious process known as forming, which involved charging and discharging the cell repeatedly for months. This made the production process slow and expensive. Furthermore, the spiral design, while offering surface area, was heavy and bulky. The Planté cell found niche applications, such as lighting railway carriages where weight was not a primary concern, but it was not yet a mass-market product capable of revolutionizing personal power. The true commercialization of the lead-acid battery occurred in 1881, thanks to the innovations of Camille Alphonse Faure. Faure improved upon Planté's design by inventing a method to coat the lead plates with a paste of lead oxides, rather than waiting for the oxide layer to form through repeated cycling. Faure created a lead grid lattice, a skeleton of lead, into which this oxide paste was pressed. This design significantly increased the surface area of the active material and, crucially, allowed the battery to be manufactured in a charged or semi-charged state. The paste adhesion meant that the tedious forming process was drastically reduced. Faure's pasted plate construction is essentially the same design used in 12-volt car batteries today. This innovation coincided with the rise of electrical generators, dynamos, and the early electrical grid. Suddenly, energy could be generated at a power plant, stored in large banks of Faure's lead-acid batteries, and used to stabilize the grid or power machinery. This was the birth of grid-scale energy storage. The most profound impact of the lead-acid battery, however, was its symbiotic relationship with the internal combustion engine. In the early days of the automobile, starting a gasoline engine was a dangerous physical task requiring a hand crank. The driver had to physically turn the engine to create compression and ignition. A kickback from the crank, caused by the engine firing prematurely, could break an arm, dislocate a shoulder, or even fracture a skull. This danger was highlighted by the tragic death of Byron Carter, a friend of Cadillac head Henry Leland, who died from complications after a crank handle broke his jaw in 1910. Leland, devastated by the loss, vowed to eliminate the hand crank. He turned to Charles Kettering of the Dayton Engineering Laboratories Company, Delco. In 1911, Kettering invented the electric starter motor, debuting it on the 1912 Cadillac. This device required a battery capable of delivering a massive surge of current, hundreds of amps, for a few seconds to turn the heavy flywheel of the engine. The lead-acid battery was uniquely and perfectly suited for this task. Unlike the Daniell cell or other primary batteries which had high internal resistance, the lead-acid battery had extremely low internal resistance. This allowed it to dump a massive amount of energy in a very short burst, the cranking amps required to turn a cold engine. This development had a paradoxical effect on the history of transportation. While the lead-acid battery was an electrical storage device, its perfection ultimately enabled the dominance of the gasoline car. By making gas cars easy to start, removing the physical barrier for women and older drivers, the electric starter eliminated one of the few advantages early electric vehicles had over gas cars. Early EVs, powered by heavy lead-acid packs with poor energy density, could not compete with the range and refueling speed of gasoline vehicles once the starting problem was solved. Thus, the battery became a subservient component to the combustion engine, a starting, lighting, and ignition device, a role it would retain for nearly a century. Even today, despite the rise of lithium-ion, the 12-volt lead-acid battery remains ubiquitous in almost every vehicle, including EVs, purely for its reliability and safety in powering auxiliary systems. Portable power, 1866 to 1980s, the rise of the dry cell. While heavy industry and automotive engineering relied on the heavy lead-acid battery, a parallel revolution was occurring in the realm of low-power portable devices. The quest was for a battery that did not spill, a dry cell that could be carried in a pocket, a satchel, or a flashlight without leaking corrosive acid. In 1866, French engineer Georges Leclanche patented a new type of wet cell that would become the ancestor of all disposable batteries. It used a zinc anode, a manganese dioxide cathode, and an electrolyte of ammonium chloride. The Leclanche cell was robust and had a relatively high voltage, 1.4 V. It found immediate success in telegraphy and early electric bell systems because it recovered well after short bursts of use. However, the Leclanche cell had a specific chemical limitation. During continuous use, the ammonium chloride electrolyte would react to form insulating compounds on the cathode, causing the internal resistance to rise sharply. This meant the battery was poor for sustained continuous draw, such as a long telephone conversation, but excellent for intermittent use, like ringing a doorbell. Early telephones often used Leclanche cells, later dry cells, located in a wooden box next to the phone to power the microphone, but users knew that long calls would cause the battery to fade. The transition to a true dry cell occurred in the late 1880s, driven by the work of Karl Gassner in Germany and others. Gassner realized that the liquid electrolyte was the primary hindrance to portability. He immobilized the ammonium chloride electrolyte by mixing it with plaster of Paris and zinc chloride to create a paste. He then sealed the entire assembly inside the zinc anode, which was formed into a cup or can that served as the casing of the battery. This design, the zinc carbon dry cell, was patented in 1886 and became the first battery that could be used in any orientation without leaking. It was a masterpiece of packaging efficiency. The zinc can served as the container, the negative electrode, and the structural support all at once. The commercial explosion of the dry cell took place in the United States. In 1996, the National Carbon Company, the precursor to Eveready, began mass-producing the Columbia dry cell. This availability of portable power sparked a wave of device innovation. In 1898, Conrad Hubert founded the American Electrical Novelty and Manufacturing Company, later Eveready, and used these dry cells to power the first electric hand torch, or flashlight. For the first time, humanity had a safe, flameless, portable light source. The zinc-carbon battery became the standard consumer battery for radios, toys, and flashlights for the next 60 years. By the 1950s, the zinc-carbon battery was reaching its performance limits. As portable electronics became more power-hungry, with the advent of transistor radios, motorized toys, and high-drain flashlights, consumers became frustrated with the short lifespan and leakage issues of zinc-carbon cells. The chemistry was prone to the local action of impurities, which caused the zinc casing to corrode and leak acid even when the battery was not in use, often ruining expensive devices. The solution came from Louis Ury, a Canadian chemical engineer working for Eveready in Parma, Ohio. In the late 1950s, Ury was tasked with extending the life of the zinc-carbon battery. Instead, he reinvented it. He utilized a manganese dioxide cathode and a powdered zinc anode. The use of powdered zinc offered a vastly higher surface area than the solid zinc can of the old dry cell, allowing for much faster chemical reactions and higher current draw. Crucially, Ury switched the electrolyte from acidic ammonium chloride to potassium hydroxide, an alkaline substance. The alkaline chemistry allowed for a much higher energy density and better performance under high drain. When Ury demonstrated the prototype to his bosses by racing two toy cars, one with the new battery and one with the old, the alkaline-powered car ran laps around the cafeteria long after the zinc-carbon car had died. Eveready introduced the alkaline battery in 1959, changing portable power forever. However, Eveready, later Energizer, was initially slow to aggressively market this premium product, fearing it would cannibalize their dominant sales of cheap zinc-carbon batteries. This hesitation opened the door for a competitor, P.R. Mallory, which would rebrand its battery division as Duracell to capture the high-end market. Duracell launched an aggressive marketing campaign focused on the longevity of alkaline cells, famously using the copper top branding to distinguish their batteries visually. This ignited a decades-long marketing war that became a defining feature of the battery industry. It was epitomized by the Battle of the Mascots, the Duracell Bunny, introduced in 1973 as a pink drumming rabbit that outlasted others, and the Energizer Bunny, introduced in 1989 as a parody of the Duracell ad. In the United States, Energizer won the trademark rights to the bunny due to a lapse in Duracell's trademark renewal, leading to the bizarre situation where the Energizer Bunny is iconic in North America, while the Duracell Bunny remains the mascot in Europe and the rest of the world. Beyond the advertising spectacle, this rivalry drove massive improvements in manufacturing consistency, seal integrity, and shelf life, making the alkaline battery the ubiquitous power source of the late 20th century. Pre-lithium rechargeables, nickel's dominance, and the hybrid bridge. While primary alkaline batteries dominated the throwaway market, the burgeoning consumer electronics industry of the mid-20th century desperately needed a reliable, rechargeable battery. Devices like cordless shavers, power tools, and eventually mobile phones and camcorders required a power source that was lighter than lead acid and renewable, unlike alkaline. The gap was filled by nickel-based chemistries, specifically nickel-cadmium, NiCd, and later nickel metal hydride, NiMH. The nickel-cadmium battery was invented by Waldemar Jungner in Sweden in 1899, the same year he invented the nickel-iron battery. Jungner's goal was to create an alkaline battery that could compete with lead acid. His NiCd design used nickel oxide hydroxide as the cathode and metallic cadmium as the anode. It was chemically robust and could deliver high currents, but for decades it remained expensive to manufacture and was largely relegated to industrial uses, such as starting aircraft engines or powering miners' lamps. It was not until the mid-20th century, with the development of the sintered plate construction in Germany, that NICD batteries became viable for consumer electronics. Sintering involved fusing nickel powder at high temperatures to create a highly porous grid. This increased the surface area of the active materials, lowered the internal resistance, and allowed the battery to be sealed without the risk of gas pressure building up to dangerous levels. By the 1960s and 70s, sealed NICD cells were powering the first generation of cordless power tools, handheld vacuums, and portable video cameras. The NICD battery, however, was haunted by a technical poltergeist known as the memory effect. Consumers observed that if they repeatedly discharged an NICD battery only partially, e.g. using 20% of its capacity, and then recharged it, the battery seemed to remember this shorter capacity. When the user later tried to draw the full capacity, the voltage would drop precipitously at the point of previous discharge, making the device fail as if the battery were empty. Technically, this was not a memory in the cognitive sense, but a physical change in the battery's microstructure. Repeated partial cycling caused the cadmium hydroxide crystals on the anode to grow into large, stable formations. These large crystals had a reduced surface area compared to the fine crystals of a fresh battery. Because the chemical reaction occurs at the surface, the reduced area led to a voltage depression. While the battery still held energy, it could not deliver it at a high enough voltage to keep the device running. While this effect was often exaggerated by consumer perception, often confused with simple voltage depression from overcharging or age, it was a real limitation that forced users to adopt cumbersome conditioning routines, fully discharging their devices before recharging them. Furthermore, cadmium was an environmental nightmare. It is a highly toxic heavy metal that accumulates in the kidneys and bones. The disposal of millions of NICD batteries posed a severe risk of soil and water contamination. This toxicity led to strict regulations, particularly in the European Union, which sought to ban cadmium in consumer products. The battery industry faced an existential crisis. It needed a rechargeable battery that performed like NICD, but without the toxic cadmium or the memory effect. The solution lay in an exotic class of materials known as metal hydrides, alloys that could absorb and store hydrogen like a sponge stores water. The development of the nickel metal hydride battery was a complex interplay of chemistry, physics, and patent maneuvering. Early work in the 1970s at Battelle, Geneva, and by Philips Laboratories explored using lanthanum nickel alloys to store hydrogen for use as a negative electrode. The chemistry was similar to NICD. The positive electrode was still nickel oxide hydroxide, but the toxic cadmium anode was replaced by a hydrogen-absorbing alloy. This eliminated the cadmium and offered significantly higher energy density. However, early alloys were unstable. They would corrode or pulverize after only a few cycles. A pivotal figure in solving this stability problem was Stanford Obshinsky, a self-taught inventor and founder of the energy conversion devices company, also known as Ovonics. Obshinsky specialized in disordered or amorphous materials. He realized that by creating multi-component alloys with a disordered atomic structure, he could create sites within the metal lattice that were optimized for storing hydrogen while preventing corrosion. His company developed specific vanadium, titanium, zirconium, nickel alloys that made NIMH batteries commercially viable and durable enough for widespread use. NIMH batteries had 2 to 3 times the capacity of NICD and suffered far less from the memory effect. They became the standard for early laptops and mobile phones in the 1990s. However, their lasting legacy was in the automotive sector. When Toyota developed the Prius, the world's first mass-produced hybrid vehicle, released in 1997, they chose NiMH batteries. The high energy density and durability of NiMH were critical for the hybrid system, which required constant, rapid cycling, absorbing energy from regenerative braking and discharging it to assist the gas engine. The success of the Prius proved that battery technology could reliably power a passenger vehicle, bridging the gap between the internal combustion past and the electric future. The history of NiMH is also marked by a controversial episode of corporate obstruction that many argue delayed the electric vehicle revolution by a decade. In 1994, General Motors acquired a controlling interest in Ovonics battery patents to use the technology in their EV1 electric car. The EV1 was a marvel of engineering, and the Ovonics NiMH batteries gave it a range of over 100 miles, far superior to the lead-acid versions. However, in 2001, through a series of corporate mergers, these patents, specifically for large-format NiMH batteries suitable for EVs, ended up in the hands of the oil giant Chevron via its acquisition of Texaco, which had bought GM's share. Chevron placed these patents into a subsidiary called Cobasis. Allegations persist that Chevron used these patents to stifle the electric vehicle market. Cobasis refused to sell large-format NiMH batteries to automakers for fully electric vehicles, only allowing them for smaller hybrid packs, like those in the Prius. When Toyota tried to use high-capacity NiMH batteries for a fully electric version of the RAV4, they were sued by Chevron Cobasis for patent infringement. The settlement forced Toyota to stop production of the electric RAV4 and physically destroy the batteries. This patent encumbrance effectively killed the large battery NiMH electric car in the early 2000s. It forced the automotive industry to abandon NiMH for full EVs and wait for the maturation of a completely different chemistry, lithium-ion. Bridge to lithium, 1970s to 1980s, from crisis to commercialization. By the 1970s, the limits of nickel-based chemistries were becoming apparent. Electronics were shrinking, and the demand for energy density, more power in less space, was growing. The next leap forward would not come from traditional battery companies, but from the oil industry, driven by a geopolitical crisis that shook the foundations of the global economy. The 1973 oil crisis sent shockwaves through the Western world. As oil prices quadrupled due to the OPEC embargo, giant petroleum corporations began to fear that the era of cheap oil was ending. In response, Exxon, then Esso, launched a massive, well-funded research initiative into non-petroleum energy sources. They created a division called Exxon Enterprises and hired some of the world's brightest minds in physics and chemistry, giving them a virtually unlimited budget and a simple directive: solve the energy problem. Among them was a British chemist named M. Stanley Whittingham. Whittingham was working on superconducting materials at Stanford before joining Exxon. He became fascinated by a phenomenon called intercalation. He found that ions of potassium, and later lithium, could slip in and out of the crystal lattice of titanium disulfide, TiS2, without changing the structure of the crystal, much like a card sliding into a deck or jam being spread between two slices of bread. This reversibility was the holy grail for rechargeable batteries. Whittingham built a battery using a titanium disulfide cathode and an anode made of metallic lithium. Lithium was the obvious choice for the anode because it is the lightest metal on the periodic table and has the highest electrochemical potential. It is the element most eager to give up an electron. The result was a 2.5-volt cell with incredibly high energy density. Exxon was ecstatic. They saw a future where electric cars powered by Exxon batteries would replace gas cars, keeping the company relevant in a post-oil world. They began commercializing the technology for small devices and even planned for vehicle integration. However, the Whittingham battery had a fatal flaw that no amount of funding could easily fix. Metallic lithium is highly reactive and unstable. As the battery cycled, charged, and discharged, the lithium did not redeposit smoothly on the anode. Instead, it built up in mossy, needle-like structures called dendrites. These dendrites would grow across the liquid electrolyte until they touched the cathode, causing an internal short circuit. Because lithium is flammable and the organic electrolytes used were volatile, these short circuits often led to thermal runaway. The batteries would catch fire or explode with alarming frequency. Whittingham later recalled that the lab had to call the fire department so often that the company management became nervous about the fire trucks at the front gate. Despite attempts to alloy the lithium with aluminum to prevent dendrites, the safety risks were too high. When oil prices collapsed in the early 1980s, the urgency for alternative energy evaporated. Exxon, looking to cut costs, slashed its alternative energy budget and sold the battery technology to licensed manufacturers. The lithium dream appeared to be dead, a victim of its own volatility. Across the Atlantic at Oxford University, an American physicist named John Goodenough was undeterred by the failure of the metallic lithium anode. He focused his attention on the other side of the battery, the cathode. Goodenough possessed a deep understanding of magnetic materials and solid-state physics. He realized that metal oxides, compounds of metal and oxygen, offered a higher potential than the metal sulfides Whittingham had used. Systematically testing materials, Goodenough's team discovered that layers of lithium cobalt oxide could intercalate lithium ions just as titanium sulfide did, but at a much higher voltage. In 1980, Goodenough demonstrated a cell that produced 4 volts, nearly double the voltage of Whittingham's cell, and 3 times that of a nickel-cadmium cell. This was a quantum leap in energy density. A 4-volt cell meant that a single battery could do the work of 3 nickel-based cells, drastically reducing the size and weight of battery packs. Crucially, Goodenough's cathode supplied the lithium ions itself. This meant the battery could potentially be manufactured in a discharged state, with the lithium residing safely in the cathode, waiting to be moved to the anode during the first charge. However, Goodenough still lacked a safe anode. Using metallic lithium would still cause dendrites and explosions. The 4-volt cathode was a revolution waiting for a partner. Remarkably, Oxford University refused to patent Goodenough's discovery, believing there was no market for it. He eventually signed the rights over to the Atomic Energy Research Establishment at Harwell, a decision that would cost the university millions in future royalties. The final piece of the puzzle came from Japan. Akira Yoshino, a researcher at the Asahi Kasei Corporation, was looking for a way to make a lightweight, rechargeable battery. He was aware of Goodenough's 4-volt cathode, but needed a safe anode to pair with it to avoid the dendrite problem. Yoshino had been experimenting with carbon-based materials. He discovered that petroleum coke, a byproduct of the oil industry, had a layered structure that could intercalate lithium ions. When he paired the petroleum coke anode with Goodenough's lithium cobalt oxide cathode, he created a battery that contained no metallic lithium. Instead, the lithium existed only as ions, shuttling back and forth between the carbon anode and the cobalt cathode. This was the rocking chair battery, the lithium-ion battery. Because there was no metallic lithium to form dendrites, the battery was drastically safer. Yoshino proved this with a dramatic test. He dropped a heavy iron block onto his new battery. A metallic lithium battery would have exploded instantly under such impact. Yoshino's lithium-ion battery simply got hot and then cooled down. It was safe, lightweight, and powerful. The commercialization of this laboratory triumph fell to Sony. In the late 1980s, Sony was desperate for a better battery to power its new generation of handheld camcorders, the Handycam, which were being limited by the heavy and short-lived nickel-cad packs. The camcorder was Sony's crown jewel, but users hated the short runtimes. Keizaburo Tozawa, the head of Sony's battery division, employed a development strategy he called range finding, inspired by naval gunnery. Instead of betting on a single chemical formula, he launched multiple simultaneous research tracks, firing shots in different directions to see which hit the target of performance and safety. The lithium-ion chemistry, carbon anode, cobalt cathode, emerged as the winner. Tozawa and his team faced immense manufacturing challenges. They had to develop new electrolytes that wouldn't decompose at 4 volts, and they had to ensure absolute purity in manufacturing. Even microscopic metal dust could cause internal shorts, but they persisted, driven by the demands of the consumer electronics division. In 1991, Sony released the world's first lithium-ion battery. The first application was the Sony CCD TR1 8mm camcorder. The impact was immediate and profound. The new battery was lighter, held a charge longer, and had no memory effect. It transformed consumer electronics overnight. It enabled the sleeker, longer-lasting mobile phones, the slim laptops, and the portable media players that would define the 1990s and beyond. Silent singularity. The history of human civilization is inextricably tied to the history of energy harnessing. Yet few milestones have been as unassuming and yet as transformative as the commercial release of a small cylindrical energy storage device in 1991. The introduction of the lithium-ion battery by Sony did not occur with the fanfare of a moon landing or the detonation of an atomic weapon, but it initiated a technological singularity that has fundamentally decoupled human activity from the constraints of fixed power sources and fossil fuel combustion. This second part provides an exhaustive analysis of the modern battery era, tracing the intricate arc from that initial breakthrough in a Japanese laboratory to the present-day reality of terawatt-hour gigafactories, diverging chemical lineages, and intense geopolitical resource competition. Before 1991, the portable world was tethered by the heavy, inefficient limitations of nickel-cadmium and nickel-metal hydride chemistries. These aqueous systems were the workhorses of the late 20th century, but they were plagued by the memory effect, high self-discharge rates, and energy densities that made truly portable high-performance computing and long-range electric mobility physical impossibilities. The arrival of the lithium-ion cell, with its elegant intercalation mechanism and high operating voltage, shattered these ceilings. It enabled the miniaturization of the camcorder, the portability of the laptop, the ubiquity of the smartphone, and eventually the resurrection of the electric vehicle, EV, from the graveyard of failed experiments. The battery has transcended its status as a mere component to become the geopolitical and economic fulcrum of the 21st century. Global demand has surged past 1 terawatt-hour per year, and the cost of storing a kilowatt-hour of energy has plummeted by over 90% since 2010, defying the inflationary pressures that have afflicted other industries. However, this trajectory has not been a linear ascent. It has been a volatile saga defined by corporate gambles, industrial policy wars, and a ruthless Darwinian competition that has seen the rise of Chinese hegemony and the stumbling of European ambitions, most notably illustrated by the bankruptcy of Northvolt in March of 2025. This part explores the depths of this revolution, examining the physics, the economics, and the politics that charge the modern world. Sony moment and the genesis of portability, 1991 to 2000. To appreciate the magnitude of the Sony moment, one must understand the stagnation that preceded it. By the late 1980s, the consumer electronics industry was reaching a plateau. Devices were becoming more sophisticated, but their power sources were not. Nickel-cadmium batteries, the standard of the time, offered a nominal voltage of only 1.2 volts and suffered from a crystalline formation on the electrode plates known as the memory effect, which severely reduced capacity if the battery was not fully discharged before recharging. Nickel metal hydride offered marginal improvements in capacity, but struggled with high self-discharge rates, losing up to 30% of their charge per month while sitting on the shelf. The scientific community had known of lithium's potential for decades. As the lightest metal on the periodic table with the highest electrochemical potential, it was the holy grail of battery materials. However, early attempts in the 1970s and 1980s to build rechargeable lithium batteries using metallic lithium anodes resulted in catastrophic failures. The metal would form dendrites, needle-like structures during recharging that punctured the separator and caused explosions. The breakthrough that Sony commercialized in 1991 was the result of abandoning the metallic anode in favor of an intercalation approach. Led by Yoshio Nishi, the Sony team utilized a cathode made of lithium cobalt oxide, LiCoO2, a material identified by John Goodenough, and paired it with an anode made of petroleum coke, a carbonaceous material capable of housing lithium ions within its molecular layers. This rocking chair mechanism, where ions shuttled back and forth without chemically transforming the electrodes, solved the safety issue. The specifications of this first commercial cell, the US-61, were revolutionary. It boasted an operating voltage of 3.6 volts, 3 times that of a nickel-cadmium cell, and a gravimetric energy density of approximately 80 watt-hours per kilogram, and volumetric density of 200 watt-hours per liter. While modest by modern standards, these figures meant that a single lithium-ion cell could replace 3 nickel-based cells, drastically reducing the weight and volume of battery packs. The first product to feature this technology was the Sony CCD-TR1 8mm camcorder, a device whose marketing centered on its unprecedented portability and runtime. If the camcorder introduced the lithium-ion battery to the world, the laptop computer made it a commodity. In the early 1990s, portable computers were cumbersome devices, often described as luggables, with battery lives measured in minutes rather than hours. The integration of lithium-ion cells allowed designers to rethink the form factor of the mobile computer entirely. One of the first commercial laptops to utilize this technology was the Apple PowerBook 100 series, specifically the PowerBook 140 and 170, released in late 1991, which benefited from Sony's battery advancements to offer a form factor that defined the modern notebook. The high energy density of lithium-ion meant that screens could get brighter, processors faster, and hard drives larger, all without reducing the operating time. This era solidified the 18650 cell format, an 18mm in diameter and 65mm in length, as the industry standard. This standardization was crucial. It allowed manufacturing lines to run at massive volumes, driving down defect rates and costs through the relentless optimization of winding speeds and electrode coating precision. By the late 1990s, the energy density of these cells had nearly doubled from the original 1991 specifications, as manufacturers like Panasonic and Sanyo transitioned from soft carbon anodes to graphitic anodes, which could store more lithium ions per unit of volume. However, this period was not without its lessons in safety. As energy densities climbed, the margin for error shrank. The industry faced its first major crisis in 2006 when Sony was forced to recall millions of laptop batteries supplied to Dell, Apple, and others due to microscopic metal particles contaminating the cells, leading to internal short circuits and thermal runaway. This event served as a stark warning. Storing high energy in a small, flammable package required near-perfect manufacturing hygiene, a lesson that would become even more critical as the technology migrated to automobiles. False start and the EV revolution, 1996 to 2015. While consumer electronics flourished with lithium-ion in the 1990s, the automotive sector remained stuck in the aqueous past. The most prominent effort of this era, the General Motors EV1, 1996 to 1999, illustrates the limitations that stifled early electrification. The first generation of the EV1 relied on heavy lead-acid batteries, which offered a meager range of 60 to 80 miles. The second generation upgraded to nickel-metal hydride batteries, improving the range to approximately 100 to 140 miles. Despite this improvement, nickel-metal hydride technology was a dead end for pure electric vehicles. The batteries were heavy, expensive to manufacture, and suffered from significant performance degradation in extreme temperatures. Furthermore, the intellectual property rights for large-format NIMH batteries were entangled in corporate acquisitions, eventually ending up with oil giant Chevron, which fueled conspiracy theories about the suppression of electric car technology. GM ultimately canceled the EV1 program, citing a lack of commercial viability, and famously crushed the majority of the fleet. The industry consensus in the early 2000s solidified around the idea that batteries were a bridge to nowhere and that hydrogen fuel cells were the only viable future for zero-emission transport. The trajectory of automotive history was altered in 2008, not by a breakthrough in fundamental chemistry, but by a radical engineering decision made by a Silicon Valley startup. Tesla Motors, observing the rapid improvements in energy density and cost occurring in the laptop market, hypothesized that a car could be powered by thousands of commodity 18650 lithium-ion cells wired together. This was a heretical idea. Automotive engineers traditionally favored large, specialized cells that were robust and easy to package. Wiring thousands of small, flammable consumer electronics cells together was seen as a safety nightmare and a manufacturing impossibility. However, the Tesla Roadster proved the skeptics wrong. By developing a sophisticated battery management system that could monitor the voltage and temperature of every single cell, and by employing a liquid cooling system that snaked through the battery pack to maintain optimal thermal conditions, Tesla achieved what nickel-MH never could, a range of over 240 miles and supercar-level acceleration. The success of the Roadster laid the groundwork for the Model S in 2012, which further refined this architecture. Tesla's partnership with Panasonic, formalized in 2009 and deepened in the following years, secured a supply of automotive-grade cylindrical cells that were optimized for durability and safety rather than just the maximum capacity required for laptops. This partnership was pivotal as it provided the volume necessary to begin driving down costs, which in 2010 still hovered around a prohibitive $1,474 per kilowatt-hour. While Tesla focused on the premium market with complex active thermal management, Nissan launched the Leaf in 2010 as the first mass-market electric vehicle. Nissan opted for a different architectural philosophy: large-format pouch cells and passive air cooling. While this reduced complexity and cost, allowing for a lower sticker price, it exposed the battery to the elements. In hot climates like Arizona, Leaf batteries degraded rapidly, losing significant capacity within just a few years. This failure underscored a critical technical reality of the lithium-ion era. Thermal management is not a luxury, it is a prerequisite for longevity. The industry largely converged on liquid cooling as the standard for practically all modern EVs, following the lessons of the early Leafs. Industrialization phase and the cost curve, 2015 to 2020. Between 2010 and 2025, the price of lithium-ion battery packs fell by an astounding 93% in real terms, dropping from over $1,400 per kilowatt-hour to a record low of $108 per kilowatt-hour. This decline is often cited as a triumph of innovation, but it is more accurately described as the manifestation of Wright's law, which observes that for every cumulative doubling of production volume, costs will fall by a constant percentage. In the case of batteries, approximately 18 to 20%. The physical engine of this cost reduction was the Gigafactory. The concept, popularized by Elon Musk but now the industry standard, refers to a manufacturing facility with an annual output capacity measured in gigawatt-hours rather than megawatt-hours. The first of these, Gigafactory 1 in Nevada, a Tesla-Panasonic joint venture, came online in 2016. By centralizing the entire production flow, from the mixing of electrode slurries to the aging of finished cells and their assembly into packs, the Gigafactory model eliminated logistical inefficiencies and maximized economies of scale. The transition from the 18650 cell to the larger 2170 format, 21 mm by 70 mm, further reduced costs by increasing the amount of active material relative to the steel casing, boosting energy density and reducing the number of welds required per pack. While the West focused on the technological glamour of Tesla, the People's Republic of China was executing a methodical industrial strategy to dominate the global battery supply chain. Recognizing that it could never overtake the West and Japan in internal combustion engine technology, China bet its industrial future on the electric vehicle. A key instrument of this strategy was the White List policy, in effect from 2015 to 2019. This policy effectively linked generous government EV subsidies to the use of batteries from a curated list of approved suppliers. Notably, this list excluded foreign giants like LG Chem, Samsung SDI, and Panasonic, effectively locking them out of the world's largest EV market during its critical growth phase. This protectionism created a walled garden in which domestic champions like contemporary Amperex Technology Co. Limited, CATL, and BYD could grow without facing international competition. They used this period to scale up manufacturing, secure upstream mineral resources, and refine their technologies. By the time the Chinese market opened up, CATL had grown from a regional player into the world's largest battery manufacturer, a position it holds to this day with over 37% global market share. This era fundamentally shifted the center of gravity of the battery world from Japan and Korea to China, where it largely remains today. Great chemistry divergence, 2020 to present. As the market matured, the one battery for all approach fractured. The industry bifurcated into distinct chemical lineages, each optimized for specific economic and performance metrics. This divergence is defined primarily by the battle between nickel manganese cobalt, or NMC, and lithium iron phosphate, or LFP. For the premium segment of the market, luxury sedans, performance SUVs, and long-range trucks, energy density remains the paramount metric. To achieve ranges exceeding 400 or 500 miles, manufacturers have pushed the limits of cathode chemistry by increasing the nickel content. Nickel is the workhorse of the cathode, providing the capacity to store lithium ions, while cobalt acts as a stabilizer and manganese provides structural integrity. The evolution has been swift, from the early NMC 111 equal parts nickel manganese cobalt to NMC 532 NMC 662, and finally the current state-of-the-art NMC 811, 80% nickel, and even ultra-high nickel variants like NMC 955. These high nickel cathodes offer specific energies exceeding 270 watt-hours per kilogram, enabling vehicles like the Lucid Air and Mercedes EQS. However, this performance comes with significant trade-offs. High nickel cathodes are chemically less stable. They are more prone to releasing oxygen at high temperatures, which can lead to thermal runaway, a self-sustaining fire that is difficult to extinguish. Consequently, these packs require robust, heavy, and expensive thermal management and safety structures. Furthermore, the reliance on nickel and cobalt exposes manufacturers to volatile commodity markets and ethical supply chain risks. The most disruptive trend of the 2020s has been the resurgence of lithium iron phosphate. Invented in the late 1990s, LFP was long dismissed by Western automakers as a low-end chemistry suitable only for power tools or city buses due to its lower energy density compared to NMC. However, Chinese manufacturers, led by BYD and CATL, recognized that LFP possessed a critical advantage: intrinsic safety. The phosphate chemical bond is extremely strong, making the battery virtually immune to thermal runaway and capable of withstanding thousands of charge cycles without significant degradation. Leveraging this safety, engineers reinvented the battery pack architecture. Instead of packing cells into modules and then modules into packs, a cell-to-module-to-pack approach, they developed cell-to-pack technologies. The definitive example is BYD's Blade battery, introduced in 2020. BYD designed long, sword-like LFP cells that act as structural beams within the battery pack. This eliminated the need for heavy intermediate module casings, increasing the volume utilization of the pack by over 50%. The result was a paradox: a battery made of a less energy-dense chemistry, LFP, that achieved a system-level energy density competitive with NCM packs, but at a significantly lower cost and with superior safety. Tesla's adoption of LFP for its standard-range Model 3 and Model Y vehicles validated this shift globally. By 2024, LFP had captured nearly half of the global market and dominated 60 to 70% of the Chinese market. Seeking to bridge the gap between the cost of LFP and the energy density of NMC, the industry has begun commercializing lithium manganese iron phosphate. By doping the LFP lattice with manganese, the operating voltage of the cell is raised from roughly 3.2 volts to 4.1 volts, theoretically increasing energy density by 15 to 20% without sacrificing the safety benefits of the phosphate structure. Major players like Goshen High-Tech and CATL with its M3P battery began mass production of these cells around 2024, targeting a Goldilocks solution for mid-range vehicles that offers 1,000 kilometers of range in premium configurations. Geopolitics of critical minerals. As batteries have become the oil of the 21st century, the supply chains that feed them have become the new fault lines of global geopolitics. The transition to green energy is material-intensive, shifting dependence from petrostates to mineral-rich nations and refining superpowers. More than half of the world's proven lithium reserves are found in the Lithium Triangle, a high-altitude desert region spanning Chile, Argentina, and Bolivia. Unlike the hard rock spodumene mines of Australia, lithium here is extracted by pumping ancient brine from beneath salt flats into massive evaporation ponds. This method, while cost-effective, is ecologically contentious. In Chile's Salar de Atacama, the extraction process consumes vast quantities of water in one of the driest places on Earth. A 2025 report highlighted that the salt flat is sinking at a rate of 1 to 2 centimeters per year due to aquifer depletion, and critical wetlands that support indigenous communities and biodiversity, including Andean flamingos, are disappearing. This environmental toll has catalyzed a push for direct lithium extraction, or DLE technologies, which promise to extract lithium without massive evaporation, though commercial deployment at scale remains a technical challenge. Political resource nationalism further complicates the picture. Chile has moved to increase state control over its lithium industry, requiring public-private partnerships that have cooled foreign investment. Bolivia, despite holding the world's largest resources, has struggled to industrialize them due to infrastructure deficits and rigid state control. Cobalt, essential for the stability of high-nickel NMC batteries, represents the industry's most acute ethical vulnerability. More than 70% of the global supply originates from the Democratic Republic of the Congo, or DRC. While the majority is produced by large industrial mines, a persistent fraction comes from artisanal mining, which is frequently associated hazardous working conditions. Even though artisanal mining's market share dropped to historic lows of less than 2% in 2024 due to depressed prices and the ramp-up of industrial giants like CMOC and Glencore, the stigma remains. This ethical liability, combined with price volatility, has been a primary driver accelerating the industry's shift toward cobalt-free chemistries like LFP and sodium-ion. While the mining of critical minerals is somewhat geographically diverse, the refining and processing capacity is overwhelmingly concentrated in China. The People's Republic refines approximately 60 to 70% of the world's lithium and cobalt and nearly 100% of the spherical graphite used in anodes. This midstream dominance gives Chinese firms immense leverage over global pricing and standards. In response, Western governments have enacted aggressive industrial policies to break this dependency. The United States Inflation Reduction Act, or IRA, has spurred a massive wave of investment in a battery belt stretching from Michigan to Georgia, incentivizing domestic production through tax credits of up to $45 per kilowatt hour for US-made battery packs. However, Europe's attempt to build a sovereign battery industry faced a catastrophic reality check in March 2025 with the bankruptcy of Northvolt. Once heralded as the EU's champion against Asian dominance, Northvolt collapsed under the weight of production scaling issues, yield losses at its Skellefteå plant, and the cancellation of a $2 billion order from BMW. It sent shockwaves through the continent, exposing the immense difficulty of competing with established Asian players who have spent decades optimizing their manufacturing processes. It has forced a grim reckoning in Brussels regarding the viability of a purely autarkic battery supply chain in the face of Chinese cost leadership. Deep Tech and the Horizon, 2025 to 2030. As conventional lithium-ion technologies mature and commoditize, the frontier of innovation has shifted to deep tech solutions that promise to overcome the fundamental limitations of the current era. Solid-state batteries, which replace the flammable liquid electrolyte with a solid ceramic, glass, or polymer, have long been the holy grail of the industry. They promise to unlock the use of pure lithium metal anodes, potentially doubling energy density and eliminating fire risk. However, they have been perpetually 5 years away for the last decade. By 2025, the technical reality is nuanced. The primary hurdles remain interface resistance, maintaining contact between solid layers as the battery expands and contracts during charging, and the formation of dendrites that can crack the solid electrolyte. Oxide electrolytes, like LLZO, offer high stability but are brittle and difficult to manufacture at scale. Sulfide electrolytes offer conductivity rivaling liquids, but are chemically unstable reacting with moisture to release toxic hydrogen sulfide gas. Polymer electrolytes are easier to process but suffer from poor conductivity at room temperature, often requiring heaters to function. Despite the hype surrounding companies like QuantumScape and Toyota, mass production of true solid-state batteries remains elusive. Instead, the industry is seeing the emergence of semi-solid or hybrid batteries, such as those used by NIO, which employ a gel electrolyte to offer some performance benefits without the extreme manufacturing challenges of all-solid systems. While solid-state chases peak performance, sodium-ion technology chases peak abundance. Sodium is chemically similar to lithium, but is thousands of times more abundant and cheap. Sodium-ion batteries utilize hard carbon anodes and cathodes made of abundant materials like Prussian white or layered oxides, completely eliminating the need for lithium, cobalt, nickel, and copper. Aluminum can be used for the anode current collector. Although sodium-ion batteries have a lower energy density, roughly 140 to 160 watt-hours per kilogram, compared to LFP, they offer superior low-temperature performance and fast charging capabilities. In 2024 and 2025, the first commercial sodium-ion vehicles, such as the Yiwei 3 and variants of the Cherry QQ ice cream, entered the Chinese market, signaling that this chemistry is viable for city cars and budget EVs. However, the most profound impact of sodium-ion may be on the grid. With the stationary storage market exploding, prices for turnkey storage systems crashed to a record low of $70 per kilowatt-hour in 2025. Sodium-ion is poised to become the dominant chemistry for utility-scale storage. This would effectively bifurcate the market: lithium for high-performance transport and sodium for the grid and entry-level mobility, relieving the pressure on critical mineral supply chains. The final pillar of the modern battery ecosystem is the circular economy. As the first generation of mass-market EVs reaches end of life, the urban mine is becoming a strategic asset. Companies like Redwood Materials and Li-Cycle are scaling operations to recover up to 95% of critical minerals from spent packs. Recycling is not merely an environmental nice-to-have, it is a geopolitical imperative. A nation that can efficiently recycle its battery stock reduces its dependence on foreign mining and refining. While capacity is still ramping up in 2025, recycling is projected to become a major source of material supply by 2030, dampening the volatility of primary commodity markets and fulfilling the promise of a truly sustainable energy loop. From the humble camcorder battery of 1991 to the colossal gigafactories of 2025, the modern battery era represents one of the most rapid and consequential industrial transformations in human history. In just over 3 decades, a niche chemical curiosity has dismantled the century-old monopoly of the internal combustion engine, reshaped the power grids of nations, and rewritten the geopolitical map. The journey has been defined by the relentless pursuit of energy density and the brutal economics of scale. It has seen the rise of new industrial superpowers in East Asia and the frantic, often stumbling catch-up efforts of the West. As we look to the future, the era of a single dominant battery chemistry is over. We are entering a diversified age: sodium for the grid, LFP for the masses, and high nickel or solid state for the extraordinary. The electrochemical singularity has occurred, and the world will never be the same again.